Our very last presentation of this automotive section here is a panel, Digital Transformation by AM for the automotive sector. And I'd like to invite Janet Carr to the stage. Janet is going to be moderating the panel, and she is the SVP of Digital Transformation at Link3D Materialize. And Janet, I'm going to go ahead and bring Taylor and Megan up if you want to introduce them, and we'll get going.
Fantastic. Hello, everyone. My name is Janet Carr. Thank you, Melanie, for the kind introductions. I'm part of a company called Link3D, which recently got acquired by Materialize. And our whole schlick is how to enable additive manufacturing factory floor through digital solutions. And now part of Materialize, there's a suite of digital systems that are out there that I'm becoming more familiar with. And we know that these tools are very helpful for supporting scale of additive manufacturing, whether it's for prototyping, design, personalization, manufacturing through supply chain execution. So I'm really excited to have here Taylor Doty from Divergent and also Megan Rock from Desktop Metal. Maybe you would like to introduce yourselves first, Taylor?
Sure, yeah. So I am the production manager for additive manufacturing at Divergent Technology. So we are currently working on executing our internal vehicle program. So if any of you guys have heard of the Divergent 21C, or the Zinger vehicle 21C car, we print most of that chassis and are also doing subframes for other vehicle companies.
And Megan?
Hi guys, my name is Megan Rock. I'm the Director of Application Engineering at Desktop Metal. At the company for about 4.5 years, and before that I spent about 4 years at Stratasys as an application engineer as well.
Amazing. And we want to bring this conversation today because we have both Taylor from an automotive company, Megan representing the hardware, and then myself on the digital side. But throughout the entire process, what we figured out, what we have decided to talk about today was explore the beginning phases of enabling additive manufacturing from part induction, design, and optimization. Then in the panel, we'll move on to manufacturing. And then we're going to follow through with what are the trends in today's technologies like AI, machine learning, texturizing tools. So let's start with part induction. Taylor, what is it like to start the process of identifying what parts to 3D print when you're looking at your car and figuring out what to build next?
So in the past, I've worked with companies where we've kind of had to scan through like something that already existed and convert a part to AM or combine parts. So that's a great place to kind of look. But since we kind of already are committed to using AM to develop subframe systems of the vehicles and stuff like that, we like design knowing that the system is going to be additive because we've kind of already like designed our 3D printed like alloys, like all of that stuff. So we kind of look at it on a system level, like what does this design need to look like? And because we kind of have our defined machines that we have available, we kind of design it to what we have in house.
Again, you come from a different angle. Desktop Metal, you guys are selling obviously machines and materials and even software systems. How do you guide organizations, especially in the automotive sector, on identifying parts to 3D print?
Yeah, so most of the time, the way that we come across the parts and the application opportunities is a customer has a problem that they're trying to solve. Sometimes those opportunities are very difficult. So we call those torture tests, where we're trying to solve something that's never been done before. And we're kind of in completely uncharted territory. And I think additive gives us the flexibility to kind of play those games. It's a really quick feedback loop. So it's worth taking a try and attempting the part and, testing it out in the application. But I think one of the things that we try to kind of focus people's energy on is one, evaluating the opportunity as a whole. So maybe you have a particular part that you have a supply chain issue, for example. That's a big topic right now. So maybe you have a supply chain issue with this particular part and you want to convert it one for one. We'll typically ask folks to kind of start with like castings or, designs that have sort of similar design designed for additive kind of techniques, right? So if it's a casting, it's usually pretty easy for us to produce that using binder jet without a lot of modifications. But there's got to be a lot of different pain points associated with that for it to make sense and be feasible for printing. So we'll give them the outline of how much it's going to cost and how many you could produce, and really kind of give them the full scope so that they can make a decision before transitioning a part. I think we hope to see more traction in like replacement parts for legacy parts, as well as, we see trim pieces. We talked about this the other day, Janet. We see trim because that's kind of low-hanging fruit, I think. But it's important to also look at the pieces that are around the additive component and look for opportunities for, consolidation of assembly consolidation or things like that as well.
Yeah, and there are tools out there. I've heard of Caster 3D, there's Trinkle. A lot of organizations are building their own DIY tools based off of the manual workflows that are being developed today and then digitizing it. What are some of the tools that maybe you have tried or explored, and what are the pros and cons of these applications?
You're talking for identifying particular parts?
Yes, that's right. Yeah.
Yeah. So a lot of times what we'll see is someone will send us a spreadsheet of parts that are a specific material and then XYZ dimensions. And maybe they're coming from their castings, right? And so they pick a material they know we have available in a bounding box that we can produce on our printers. And then they already have the cost to manufacture. So they'll just send that to us and ask us to quote it. And a lot of times we can produce those parts, but it might not make the most sense to produce those parts. And so it's it ends up being a very manual process, because even if you can kind of, drum down to like the parts that could be produced based on material and part size, like I said, you want to be able to optimize the parts, add more value, light weighting, especially for automotive, right? Improving fuel efficiency by light weighting components. Being able to show that additional value is really important. And so right now it is a manual process. Somebody is a champion within those sites. A lot of times these automotive OEMs have entire teams dedicated to this, and it's their job to kind of, locate those opportunities and bring them to the OEMs.
Mm-hmm. And Taylor, do you have any experience with tools like these?
So not in my current job, but previously, when I worked at GE, we did go through and try to like identify the components. And for us, it was really important, like Megan said, that even though maybe the cost to manufacturing might go up or be the same, it's important to kind of work with your organization to assign like cost for like not for light weighting. Like if that is really important, or like maybe your supply chain got smaller because you're producing it in-house versus going through a supplier. So I think like thinking of those trades, because it is really easy to kind of just look at how much you're paying for it now, and not really think about, but if I combined 3 parts. So kind of thinking not just at a single part level, but more at a system level, supply chain level thinking is very important in identifying these parts.
Yeah, definitely. And Matt, thank you for mentioning that Caster 3D, Trinkle, and Twicket are great, amazing companies. So organizations out here, if you're looking for ways to digitize some of the business calculations for comparing like traditional costs versus additive manufacturing cost, design for additive manufacturing, and other factors that might help you identify what parts could be considered for 3D printing, those are definitely some solutions to look into. So moving on from part induction, now let's say you finally chose your part, now you're designing your part. What are some of the favorite tools that you guys are using design for different types of applications for additive with regards to automotive? Because in automotive sector, as we saw in the Rivian presentation, you've got small parts, you've got large parts where you need to have some different cuttings and glue them back together. I know Magix has great tools for that. But there's also texturizing tools so that when you're doing your prototypes, you can actually model out a realistic, leather experience versus, whatever it might be to help you get to that level of realism to hopefully bring this prototype to the manufacturing side. Taylor, anything you'd like to share on your favorite design tools and what features have helped you?
I use a lot of Materialize actually.
Oh, really?
Yeah. I mean, I think we use standard CAD. We also at Divergent we have a software team that we're working with because there's like a lot of intersection between analysis, topology optimization, build. So we kind of see that there's like a little bit of a loop between the people that are designing our parts and then the people that are making them. So we kind of try to connect everyone. So we do have some internal tools because we look at it as kind of a whole system level, and we kind of really like to like plan out our whole build. So like a big thing for us is like how productive can we be? Because we're using powder bed and we really want to be as productive on those machines as possible. So that's a big factor too. And how like and if you look up our company, we basically divide these subframes into components and are automatically assembling them. So like how do you divide them efficiently to get good like build numbers and that type of thing. So we have software geared towards that. But for build preparation, I definitely use a lot of Magix tools. That's probably my main go-to one. I know like Topology is really awesome. I've done a trial with that. Dendrite is really great. We're in like a partnership with them, like a development partnership with them.
Can you talk a little bit more about that regarding like solutions like Dendrite or Topology for those that don't know what these technologies are?
Yeah. So Topology is a tool where they have. I don't have as much experience with it, but it's a very great tool in terms of processing, like being able to pull up like huge models, generating lattice, generating self-supporting structures in different areas. So kind of like a very good like CAD tool. I know like back when I did more design engineering, we would manually like design one cell of the lattice and like propagate it in NX, and it would take forever. And I did all my supports in NX and it would take forever. So there's so many tools now that make it less painful for you. So I would say to not do that because that, it made my life very awful. Wait, what was the other thing? Oh, Dendrite is very good with, and I think a lot of other softwares are developing this way, but like automating build processes. So like a lot of companies, like when they have a part, they eventually want to have like an automated build every time where either automated labeling or like automated selecting surfaces that need support. And so like Dendrite really brings a lot of like coding interfaces that are accessible for everyone to kind of automate a lot of these tasks where you may not need really a lot of skill, but it's something if they're done incorrectly, like if something's labeled incorrectly, it just multiplies like throughout the entire manufacturing process.
Yeah, and that becomes really important when you're doing serial production and you want to make sure that every part is made the same way. Yeah. And Megan, how about you? Like, what do you tell the newbies that are coming into this? What tools to get started with? And then for those that are more advanced, I know you have a new solution called Live Sinter. And you know, a lot of folks say that, you know, oftentimes design for additive manufacturing is siloed from manufacturing itself. And there's a need for creating that feedback loop because when you're designing for additive, it's not just for printing, but all the post-processing, finishing, and QC that happens afterwards. Can you share a little bit more about how you can bring the downstream process to the front end?
Yeah, I'd love to. So I also use Magix. Like I can't function without it. So it's that bad. But I use Magix for, you know, if I'm playing around with nesting densities and I want to kind of tweak things to see if I can fit more parts in, or we actually can build, we have a plugin for desktop metal support generation. So if you want to create your own supports in Magix, you can do that as well. So I use that a lot. One of the other softwares, like you said, Live Sinter, is really interesting because for the binder jet process, the place of highest risk for us is actually in sintering. It's not during the printing process. So we're not building up forces. We're just gluing together metal powder particles. So where things get tricky is in the furnace. So I can take a part from a customer and I can choose what I think is the best orientation that I'm going to sinter that part in. and I can actually just run a sintering simulation that basically applies all of the forces that the part's going to see during sintering. So that would be things like, gravity, the frictional force between the bottom of the part and the plate that it's sintering on. And there's a bunch of other different parameters that it's going to measure for and account for. And you basically run a sintering simulation, and you can watch how the part behaves. And then you can generate supports either in Live Sinter or in our slicing software that comes with our equipment called MFG, or in Magix. Like I said, there's a lot of different ways you can generate supports, but you can look at how the part is going to behave in the sintering process, and then you can sort of support in those areas. Live Sinter also is able to negatively offset the geometry. So it's basically going to look at how something's going to behave during the sintering process. It's going to negatively offset it. So basically distort it in the opposite direction to compensate. And then it's going to rerun the simulation. So it does it 5 times so that, because, after you pre-distort the geometry and then you sinter it again, you have a different physics problem, because, something that used to be, level is now pointing upwards. And so it'll run it over and over again until it reaches the appropriate negative offset. And it takes the guesswork out of which position should I be sintering this in, what kinds of things are going to go wrong. I've had several situations where I've had, issues with parts and run them through Live Sinter and been embarrassed to say to customers, well, as you can see here, this is what happened in the furnace. And had I checked it before I printed it and sintered it, I would have been able to, catch that. So I like to use it before I even generate supports or anything, just to see how things are going to behave.
That's fantastic. And Taylor, do you often do this as well with laser powder bed fusion technology?
So yeah, we've used a few build simulation tools because our parts are hollow and very thin wall. We kind of did not have a lot of success with the out of the box tools, and also we are developing our own alloys and our own parameter set. So we had tried to kind of use some of the out the box simulators. Currently, we really look at or kind of developing our own algorithm where we're mostly looking at results of printed parts with no compensation. So we do laser powder bed is slightly different, because instead of gluing the powder particles together and then sintering them, we are basically welding layer by layer. So you do see a lot of thermal distortions, and it can happen, and there's orientations too. So I know Materialize has a plugin, and a lot of them really show you the trends correctly in terms of using it exactly to offset the surface. We just haven't found enough success with it. So we basically will actually print our parts and kind of compensate based on that. But not to say that you can't develop that. That just hasn't been where we've focused a lot of our time on at Divergent.
Yeah, it's really interesting, because last time when we chatted, especially when we talk about manufacturing, there's folks like Bello 3D who have launched the Sapphire technology, where there's in-situ monitoring of the print, and then it automatically corrects the print to make sure you have highest quality output. And so is Markforged doing it with the Eiger technology. Is this something you think all equipment manufacturers will end up adopting? Megan, I was curious what you think of the pros and cons with in-situ closed feedback loop type equipment.
Yeah, so today for the binder jet side, we take images of every printed layer. We take images from top lighting and side lighting, so we can get different, we can see different things based on the way that we light the build up. And then we could compare that with the build slices, but today, most of the software developed is assuming that the printer is, behaving normally. In terms of in situ or during the printing process, right now there isn't anything that's actually checking to make sure. But you could imagine if you look at a layer and then you look at what's actually printing, you could imagine capability there.
Mm-hmm. But sometimes, like Taylor, so one thing about laser powder bed fusion is you can check layer by layer, but sometimes when you do the post-processing, the heat treatment in the hip, like maybe the issues might have resolved itself, right?
Yeah. So we see that. We're definitely looking into Insitu monitoring, and I definitely think most machine manufacturers, that's my cat, have most machine manufacturers have some type of in situ monitoring that they're offering. And I definitely think the technology of that's going to be good, but there are some things where you might not see it because the process may have gone as intended, but the internal stresses within your part could have caused cracking like further in the build. And that's just where you don't see it because it's buried under the powder. So I think even though we're getting really good and it's really exciting, there's still like mysteries that happen during the process that you might look through all your sensor data and we collect and real-time monitor a lot of our sensor data, and we'll have a part that comes out and it becomes really hard to root cause. So it's still really important, like all the engineering principles with understanding the manufacturing process you're choosing, like your part geometry, your part material, all that stuff.
Yeah, and that's why it's really interesting because I've been advocating for digital platforms for additive manufacturing for the last 5 years. And it's interesting to see how, you got like general MES systems that don't work very well for additive manufacturing because the data model isn't designed for additive, where, additive manufacturing, you got parts that are splitting, combining together, going off on their own paths. And so when all the data gets to be connected and tracked and traced, there's so much interesting opportunities for analyzing this information to figure out what the root cause might be. But like you mentioned, the root cause can come from anywhere. Did it come from design? Did it come from, preparing the build? Was it the environment, manufacturing? So being able to capture that data is probably helpful.
Yeah, I agree.
On that note, while we're still on the simulation-ish discussion, Sam or Allen wanted to ask, what software do you use for motion simulation? Is that something you use?
For motion simulation.
Or do you ever use tools like ANSYS for doing
Yeah. So we mostly use like HyperWorks type software for like stress analysis, load analysis, and we have like a crash team that probably use, I'm not 100% sure, but they probably use like Elastina to do the nonlinear crash analysis. I'm not as involved with that. I'm mostly looking at anything to do with like build simulation or the part geometry types.
How about you, Megan? Especially when folks are building manufacturing parts, what type of simulation software might be helpful for binder jetting technology?
So I don't know. I tried to get confirmation if I could talk about this beforehand. It was a project that we did with another company, but I can tell you that folks are working on software that basically helps designers to optimize for the process. So there's different technologies. For example, if you're going to be producing a part via casting and you want to optimize the topology for a particular load case, it can consider the manufacturing process you intend to use, and it is not going to give you a final design. It's going to give you a really nice starting point of the design optimized, and then you kind of have to go in and manually tweak things. So it's still an iterative kind of manual process, but it starts you in a place where you wouldn't have been without the topology optimization side.
Understood. And while we're talking about topology optimization, which requires a lot of data and data processing, how do you think AI, artificial intelligence, and machine learning can be applied in additive manufacturing, whether it's from the design, the manufacturing, or post-processing side of things?
Yeah, I mean, definitely to stop a build when you're seeing issues. A lot of machines already kind of have that built in, where if it sees an issue on the like post recoat photo, it'll like try to recoat a few times. So I think that's kind of something already in place. Sorry, your question was AI stuff, just how it can be used in
Yeah.
Okay.
Yeah.
I mean, we're really using all of the sensor data to really track, for example, when we need to change filters. That's not really AI. Like right now, we're doing it a lot and using automated tools, but not really putting in that. There's a lot of burden on the operators, for example. Like I have all these dashboards that I've built that turn red or turn green. But it does like leave room for automation. So I definitely think there's room to improve.
Yeah, I personally still think, like, after talking and working with so many different organizations, we're not necessarily at the stage of all using AI and ML yet, but maybe the first stage is data collection and having a clean data set so you could make sense of the information. But over time, as we progress and understand what this data tells us, there could be more opportunities for using AI and ML for like predictive maintenance, or even potentially if you integrate with a powder management system, being able to understand like how many times could you recycle this material, and how can we potentially get to not having to I don't know, throw away our stash and refreshing that in the future. Is it possible? I know some organizations have gotten there, but if that could be made easier for everyone, that could help save costs for a lot of organizations, let's say.
Oh yeah, I remember doing calculations, and like I think at least where I was, it was like 10 times it could be reused. The SLM machines are interesting because they self-sieve, so it's almost like continuously reused. So yeah, I think that's very interesting in the powder handling over time, and as you get larger and larger machines, like how that works.
Yeah. Do you have thoughts on that, Megan? Speaking of larger machine size and
Yeah,
material
binder
reuse?
jet, we keep reusing. We reuse our material 100%. So, you know, we take out obviously anything that's been partially bound, but we are reusing the material 100%. And I know there's definitely sort of best practices. It's a manual process at this point where, you know, you're putting test specimens in every build, and you can, you know, manually measure and make sure that nothing is out of range. And then you can tweak accordingly. So it's still a manual process. But I mean, as we get towards, you know, more automation, like you're obviously for binder jet right now, there isn't a whole lot of, you know, automated depowdering and things like that, but there needs to be. There's definitely a need there. So the industry is definitely going to go in that direction. And when it does, then maybe there are ways that you could pull those, you know, density cubes or specimens out of the depowdering process and throw them into a separate place where they get some sort of analysis done.
Yeah, most definitely. And speaking of that, we actually have one of our top voted questions, kind of aligns with
Depowdering.
the challenges you talked about. Not necessarily depowdering, but what are some of the technology gaps you see for industry that we need to all address? You mentioned, Megan, depowdering. Are there other technology gaps we need to address for the automotive sector or in general?
Well, material development, there's a big push on the material development side, at least in the binder jet, you know, kind of technologies, because the automotive sector typically shies away from stainless. There's obviously particular applications where stainless steels make sense, but when we talk to every automotive OEM and we say, you know, we can offer stainless, there's pushback because of joining, you know, complications, how it interacts with other materials. So material availability is huge. What materials we're able to produce. We are pushing very hard in that sector right now, because we know that that's going to be a focus in order to make the industry successful. So yeah, that's a big one. Depowdering, like I said, that's a big one. Our process requires sintering furnaces. So there are sintering furnaces available today, but there could be advancements made there as well.
Yeah. What are your thoughts on that, Taylor?
I mean, I would say a lot of the same things Megan's saying. I mean, we use a Solucon depowdering system, so like an automated gantry system. to basically vibrate a build plate and move the part around. There's even technology that can look at like your internal passageways. But for us, our passageways are very complex, and we put tons of parts on a build plate. Like that's our goal. And so we still, even with automated systems today, really struggle with really getting all the powder out of our parts. And then also the support processing, like another software program that I didn't mention, but CADS, I think it's called CADS. It has like there's different support structures where instead of just being uniform from top to bottom, like it'll have more openings at the bottom and get more dense to the top. Materialize has like the E-stage supports. So like those are helpful, but then still it's hard to, if you're producing a lot of different styles of parts, it's hard to have an automated way of removing support. So you end up having to really rely on a lot of manual very skilled people that aren't going to damage your parts to remove supports. So those are the two big things that I struggle with in my role as managing the production at Divergent.
Those are really important ones. Imagine a day where you can just hit print, but we're probably that will never happen. Or maybe I'm a little bit jaded.
Well, and it's like the support material, you want to be able to back into powder, right? Like eventually, because all of this stuff is waste, and sometimes you need really dense supports to be like, in my process, to be like a thermal conductor. So that's something, as we're really focused on the environment, that's something like we really think about deeply at Divergent.
Yeah, speaking of materials, we have an anonymous question that came in. What are the top 3 alloys you're using? And Megan, what top 3 alloys do you see automotive sector wanting to use?
So low alloy steels are typically what we're being asked for. I think that we'll see quite a bit of traction in the Inconels, so the super alloys. I think that we'll see some traction there. And then we still get some asks for stainless. So like interior trim components and things like that are being done in stainless steels.
How about you, Taylor?
Yeah, so we spend a lot of time developing our own aluminum alloy. So we're mostly looked at many different aluminum-based alloys that are okay for crash. So that's really like our materials department. That's what they're focused on. I would say we mainly print aluminum, probably about like 90%. But we we have like a great powertrain team. And so with that, we've utilized cobalt, chrome, and Inconel, which are kind of overkill for what it is, but they're established parameters. They kind of came up in the aviation industry. So we feel really comfortable like pushing the limits and designing with them. It can print at really thin walls. So we use that. It might not be the exact tool for the job, but we had been using some titaniums, but with the powder bed and the thermal distortion, it's not, we typically with the parts that one hasn't worked out as well for us. So we're mostly on the powertrain, we're on the Inconels, and then for everything else, we're on aluminums.
Understood. I hope everyone gets some of those nuggets. Speaking of distortion, another question that Kritagya Kumar asks, simulation result obtained from software are 100% accurate, or we can see a big difference? Kindly comment as per your experience, specifically for direct DMLS process. I guess that one's for you, Taylor.
So the trends are typically accurate, but the magnitudes are not. Typically they use, it just assumes like a linear, it's like a strain-based analysis, and it's not totally right. And it is chunking your part down because it can't solve every layer of your build. So like, I know that people have used them for compensation in the past, but for us really like, and then those softwares will have you run a calibration build where you're building test bars and then you're like cutting them and measuring distortion. So I would say like, it's important if you're using those to follow their like documented calibration process. And then really it gives you really good trends. And I think you can play around with it and get your model depending on the type of parts you make. Like we've had it be very accurate for solid parts. But once you get into more hollow geometries where you're really like making especially like if we have stuff that are like less, like about a millimeter thick, and because it's not putting that many elements through the thickness, or it's like giving you these voxels, like we have not had success with it being accurate. But it is a great tool. Like I would definitely use, I know Materialize has one where you can like run your build and it'll show you the hotspots for distortion. You might want to tie them down with, I would use it or that's how I use it in my job.
Mm-hmm.
I'm sure other people have maybe figured it out or use it in different ways.
Yeah, for the center-based stuff, we have to use it. There are certain geometries that we can't do without it. So,
yeah. Thank you for that question. And that brings us to another question. You mentioned automation. Have you already automated your machine hardware? And if not, where do you see the highest potential? So I guess there's many angles to this, automating your machine hardware from sieving to manufacturing, then post-processing, or where is automation being introduced? And where are the gaps?
Do you want me to start, Taylor?
Yeah, sure.
So I think, like I said, depowdering is a very obvious one. And I think also inspection. I think that there needs to be a bit more on the inspection side, whether it's by scanning for dimensional or X-ray, things like that. Ways to automate that would be ideal. It's not something that we have that we like offer or like guide people towards today, but it would definitely help with the process. You could imagine something placing, depowdered parts, preparing them for sintering, and then that going through and being scanned automatically, and then, alerting you if there's anything going wrong.
Mm-hmm. On that note, is there any kind of X-ray CT scan that works very well with additive manufacturing metal technologies, or where do you start if you were to explore that further?
Taylor, you want to take this one?
Yeah, sure. So we, I don't remember the exact tools we use, because that once it leaves AM production, I look at the results, but I'm not the one actually doing the analysis. But we do have a CT scanner. Mm-hmm. Currently, we do use it for everything right now, and we can fit all of our nodes in there, and it's really important, especially when you're doing alloy development, to really make sure you're not seeing any micro cracking or anything, any porosity. So we do utilize our CT scanner a lot, and then we use a lot of we like ferro arm scan our parts at a part level, and then we even are having larger machines to look at it at an assembly level, because we really need to take a lot of that printing data and kind of it feeds into our assembly process. We have a meter scanner for CT, and then we have a ferro arm. We use the GOM. We have a bunch of different scanners, and the scanners help us with just kind of fine tuning our simulation. So sometimes when you run the simulation, it's close, but it could be closer. So we have what's called a scan offset capability in Live Center. So if you have a scan of the part that, Live Center produced, or that you ran a first pass on and you forgot to Live Center it, you can take a scan of it and then put that into Live Center, and it'll compensate accordingly. So we use both of those as well.
Yeah, that'd be really interesting. Like if you ever go to the Renishaw facility, they showcase their CNC machines, but there's automatic like CMM, dimensional accuracy measurement going on. So the system gives like feedback loops, so it will end up machining the part to like hopefully near net shape. Regarding CT scanning or X-ray CT scanning, it seems like that industry is getting a little bit more revamped these days. I know there's a company called Meter, and they have a very great like UI browser user interface so that folks can actually collaborate more efficiently, as opposed to back in the days, like applications were pretty siloed. Do you think this is going to happen across all other post-processing and QC equipment, going digital and providing better platforms for people to get higher quality output? Wondering what trends you see on that side.
Yeah, I mean, I think that would be great. Like currently we're using systems where we'll get like a point cloud of the results, and it kind of, we like have limited licenses. So it is hard for people to just see the results. Like kind of what I see in my day-to-day is I really have to go back and forth if I want, because sometimes I won't want something best fit. I'll want it fit in the build orientation to see like, oh, did that support hold this feature down like I thought, or something like that. So yeah, I definitely think that it would be useful. And when you CT scan, you get these like huge results sometimes, and it you do have to have a certain set of skills to use those machines. So yeah, I do think that would be a great trend going forward, and it would make working a lot easier because yeah, I mean, that's kind of your scorecard on, right, if you're producing a part is your scan results. That's like kind of part of if you're doing a good job.
Mm-hmm.
Another question came out from Desktop Metal, so Megan Rock, get ready. From Adiola, part numbers and machine qualification are important when migrating to AM. Will you be able to comment on part approval processes that you find useful for your customers?
Part improvement processes.
Part approval.
Yeah, so part improvement could be lightweighting. Is she speaking? Can I see the question? Oh, here it is.
Yeah, it's part approval. Sorry.
Yeah, so part approval process, basically we're looking at parts. We'd like to see parts that are feature rich. Of course, the material needs to make sense for the application. We'd like people to understand the capabilities of the system so that they can understand, if we are not able to hit a certain tolerance, that they're going to need to do post machining. I usually tell people, like, if you need a precision ground tolerance, you're going to have to precision grind that surface because we're not going to hit that type of tolerance. So we usually try to evaluate the parts and really set expectations so that everybody understands all the different costs, understand the cost of what you would have to produce this using a conventional manufacturing method versus our cost. And so even if there is maybe post machining or things like that, you are probably still doing that on the other side. So maybe you reduce your steps from 16, setups to 3 setups. So we try to just properly set expectation. And I think there's also, with any manufacturing process, there's design rules, and this, additive is no different. And, the powder bed fusion side is going to have a different set of design rules than we do. So a lot of times when people come to us with, they have powder bed fusion backgrounds, they're making decisions that do not lend themselves well for sintering. And so, getting to understand what the design rules are helps people to properly identify parts.
Any comments you want to add there, Taylor? Especially as a customer yourself, what are the implications that you put on your suppliers?
Yeah, I mean, we are kind of so we develop materials, but we're working with suppliers, for example, to produce our materials or people to supply our machines. So like kind of coming up with what our requirements are can be hard because sometimes we're just working off of data we have or theoretical data.
I know we're almost down to a close, so we have 2 minutes left. So feel free to upvote your favorite questions because we're going to look at those now. All right, Kritaya Kumar, another question from you, the last one. Do you guys have observed any dimensional variation after metal powder has been used more than 10 times, specifically on the downskin surface? Very, very specific here.
This is a powder bed fusion question.
So because our machines, so we do not, we are designing our powder to be design our systems are so that we're continuously reusing powder. They're sieving systems that are kind of keeping out the too large particles. And we are monitoring dimensions. I would say that we have a kind of a tolerance that we've developed based on a lot of prints. I don't know if we've actually tracked it through how much the powder has been used. It's actually something that we're working on is actually collecting more powder data over time on our builds. That's something that kind of that we are working on more towards this year. But yeah.
That's fantastic.
Yeah.
Well, on that note, thank you, Taylor and Megan, for sharing your insights and letting us grill you on all your digital tools. It seems like there's so much digital tech stack out there that someone might want to learn in order for them to become great contributors to the additive manufacturing group beyond managing machines, processing the post-production activities and design. Anything else you'd like to add regarding other digital tools that you might want to add to your tech stack to become a well-rounded additive manufacturing user?
I think, I mean, if you don't have resources to do metal printing at your company, I think like honestly having a plastic printer that you're practicing on or being good, depending on what area you want to work in. I would say like CAD if you want to do designing, or like buying your own printer and setting it up. I mean, the mechanics are always different, but just getting like hands-on experience with the design and machine tools.
Thank you. And last words, Megan, before we close this channel?
Yeah, thank you for having me.
Yeah, thank you.
Fantastic.
Great.
So if you want to meet Taylor and Megan later, feel free to find us in the virtual networking floor. Otherwise, reach out to them via LinkedIn. I will now hand this back over to Melanie. So Taylor and
Thanks so much,
Megan,
Janet.
turn off our cameras.
Thank you.